My name is Vernika Gaduri, and today we will be solving a linear algebra word problem through a matrix and a parametric solution. First, we're going to identify the word problem. Nina is playing a board game similar to Candyland with a friend. In this game, a player rolls a die and moves however many times the die's pip displays. A player's point total can go up, down, or remain the same depending on the point value corresponding to the square the player's piece lands on. However, Nina has lost the instruction manual and does not know the worth of each of the 4 squares: blue, red, yellow, green. And now all she has are the old records of previous games she has played. In one game, 1 blue square plus 1 red square plus 5 yellow squares plus 3 green squares summed up to 47 points. In another game, 2 blue squares plus 2 red plus 2 yellow plus 4 green totaled to 41. And in the third record, 3 blue plus 7 red plus 9 yellow plus 12 green sums to 141. Based on these recordings, how many points is each square worth? Okay, so now we're going to start by assigning variables to each of the colors so that we're able to construct a proper system of equations. And so we're going to say that for each color, we have a letter, so W equals blue, X equals red, Y equals yellow, Z equals green. And then we're going to set up a system of equations, so the coefficients are going to be the occurrences of each square within each game or each record. And then those occurrences will add up to the point total that the game record ascribed. And so we don't know how many points each square is worth, but we just know these 3 different games. And so we'll then set up a matrix and row reduce it in order to figure out what the point total is worth. And so that is our reduced matrix, our starting matrix with the coefficients that we have assigned each of the variables. So we're going to start row reducing in order to get a parametric solution. And so first, we're going to do the Gaussian-Jordan method, which is finding a leading coefficient of 1 on the first row and the leftmost row, and then we're going to work downwards and make sure that all the rest of the numbers in the column are zeros. And so the best way to do that is by taking the row that has a leading one and then using multiples of that in order to simplify the rest of the numbers in the row, and so in the rows. And so as we see, we have R2 equals R2 minus 2R1, and a similar method is applied in the next step. And so a similar grasp of that method is used, and except with R2 swapping with R3, we're using that method because it's easier for the Gaussian-Jordan method if we have a non-zero where we want our leading 1. And so we're going to swap those 2 rows in order to have that 4 in the entry there. And so that will follow. And then in part 3, for the third column, we simplify in a similar way, and we're left with a column that we cannot have a leading 1 in because it would disturb the other 3 columns' leading 1s, and that would not be in row reduced echelon form. And so we're just going to say this is our row reduced form, and we have both the fractional form and the decimal form. And from this, we can now construct our parametric solution. And so because there are more variables than rows, we actually can't have a unique solution for each square. We have to parametrize. We can't have just one, like a number for each of the variables or each of the squares. So that is going to lead us to parametrize. And so by using the row reduced form, we assign a equation for each of the rows. And so in the first row, we had the leading 1 is W, so that's the blue square. So 1 blue square plus 5/8 of the green squares is equal to 63 over 16, and so on and so forth. And then for the parametric solution, we want to make sure that every variable is has a solution on the right side and the variable stands on its own on the left side. And so Z equals T, we set that as the parametric. And so we simplify, and the rightmost is our final parametric solution. We set Z as the parameter. We can set it for any variable, but we choose to do Z, and is a line in R4 because there's 1 parameter for each variable, and there are 4 variables, so it's R4, and it is a line. And so the solution means that the point value can actually be any number between negative infinity and positive infinity because the word problem states that the point total can go up or down. And so we can choose any number in this range, and it will not affect the validity of our solution. And so this will be a good range that we can have in our parametric solution. And so no changes were made in the matrix, just in the writing of the word problem. And so that would be your final solution. Thank you so much.